Right now in a lab, a machine is solving a problem that would take every computer on Earth working together longer than the universe has existed. And it's doing it in about 5 minutes. That's not science fiction. That's a quantum computer running today. And if that sentence doesn't stop you in your tracks, it should, because we are talking about a device that doesn't just compute faster than everything that came before it. It computes differently. It doesn't play by the rules that have governed every calculator, every laptop, every supercomputer since the dawn of the digital age. It plays by a completely different set of rules, rules borrowed from the strangest, most counterintuitive corner of physics ever discovered. And by the end of this video, you're going to understand exactly why that matters. Not just for scientists in white coats, but for you, for your bank account, for the medicine you might take one day, and for the very security of the digital world you live in. Let's start with the machine sitting in front of you, or in your pocket, right now. Your phone, your laptop, every computer you've ever touched, all of them speak the same basic language. That language is built from bits. A bit is the smallest unit of information a classical computer understands, and it can be one of exactly two things, a 0 or a 1, off or on, no or yes. Every photo you've ever taken, every song you've ever streamed, every word of every email you've ever sent, all of it underneath the surface, is nothing more than an enormous, almost incomprehensibly long string of zeros and ones. Your computer processes these strings one instruction at a time, incredibly fast, billions of times per second. But fundamentally, it is still doing one thing after another, just at a blistering pace. That speed has been enough to take us from room-sized machines that could barely do arithmetic to devices that fit in your palm and can render entire virtual worlds in real time. But there is a category of problem, a very specific and very important category, where no amount of classical speed will ever be enough. Not in 100 years, not in 1,000, not if you built a computer the size of the solar system. These are problems where the number of possibilities explodes so quickly that brute force checking becomes physically impossible, even for a machine that never sleeps and never makes a mistake. This is where quantum computing steps onto the stage, and where the story gets genuinely strange. A quantum computer doesn't use bits. It uses something called a qubit, short for quantum bit. And on the surface, a qubit sounds almost identical to a regular bit. It can represent a 0, and it can represent a 1. But here's where everything changes. A qubit can also exist in a state that is neither purely 0 nor purely 1, but a blend of both at the same time. This is called superposition, and it is not a metaphor, and it is not a trick of language. It is a real, physical, measurable phenomenon that has been demonstrated in laboratories again and again for decades. Picture a spinning coin. While it's in the air, spinning, it isn't really heads or tails. It's something in between, a mixture of both possibilities, and it only becomes one or the other the instant it lands and you look at it. A qubit behaves a little like that spinning coin, existing in a rich mixture of states right up until the moment you measure it, at which point it snaps into a definite 0 or a definite 1. That in-between state, that blend, is where the power begins. Now, here's the part that turns a curious quirk of physics into a genuine computational revolution. When you have one qubit in superposition, you have access to two possibilities at once. That alone is interesting, but not earth-shattering. But quantum computers don't use one qubit. They use many, and here's the key. When you link multiple qubits together, the number of possibilities they can represent simultaneously doesn't add up. It multiplies, and it multiplies exponentially. 2 qubits can represent 4 states at once. 3 qubits can represent 8. 10 qubits can represent over 1,000 states simultaneously. 50 qubits can represent more states at once than there are stars in the observable universe. And modern quantum processors are already working with well over 100 qubits, entangled and coordinated together. What that means, in practical terms, is that a quantum computer isn't just checking possibilities one at a time, faster than a classical machine. In certain carefully designed algorithms, it is exploring a staggering number of possibilities all at once, in parallel, using the fundamental fabric of quantum mechanics itself as its workspace. This is the heart of what people mean when they say quantum computers are exponentially powerful. It isn't marketing language. It's a description of how the mathematics of superposition scales. But superposition alone doesn't explain the full picture, because having a lot of possibilities floating around is only useful if you can actually coordinate them, combine them, and extract a meaningful answer at the end. That's where the second pillar of quantum computing comes in, and it might be the strangest phenomenon in all of physics: entanglement. When two qubits become entangled, their fates become linked in a way that has no classical equivalent whatsoever. If you measure one entangled qubit and find it in a particular state, you instantly know something certain about its entangled partner, even if that partner is sitting on the other side of a room, the other side of a building, or, in principle, the other side of the galaxy. Albert Einstein famously distrusted this idea so much that he called it spooky action at a distance, convinced there had to be some hidden, more sensible explanation underneath it. Decades of increasingly precise experiments have proven him wrong. Entanglement is real. It has been tested, retested, and confirmed under conditions specifically designed to rule out any simpler classical explanation, and it holds up every single time. In a quantum computer, entanglement is the glue that turns a pile of individually spinning coins into a single unified computational system. Entangled qubits don't behave like separate independent objects that happen to sit near each other. They behave as one interconnected whole, where operations on one qubit ripple through and affect the entire entangled group. This is what allows quantum algorithms to coordinate an enormous space of possibilities and steer them toward a useful answer, rather than just generating a chaotic soup of random outcomes. Superposition gives a quantum computer access to a vast landscape of possibilities. Entanglement is what lets it explore that landscape as a connected, coherent system, rather than a scattered collection of unrelated guesses. There's a third concept that's just as important, and it's the one that actually makes quantum algorithms work in practice: interference. This is where quantum computing goes from strange to genuinely clever. Because a qubit exists as a wave-like combination of possibilities, those possibilities can interact with each other, the same way ripples on a pond interact when they overlap. Where two ripples align, they reinforce each other and grow taller. Where they're out of step, they cancel each other out and flatten. Quantum algorithms are engineered with extraordinary precision to make the wrong answers interfere destructively, canceling each other out, while the right answers interfere constructively, growing stronger and more likely to appear when you finally measure the system. In other words, a quantum computer isn't randomly stumbling through a haystack looking for a needle. It's using the wave-like nature of quantum states to make the incorrect straws fade into the background while the needle itself gets amplified. That is the real secret behind quantum speedups. It isn't just about having access to many possibilities simultaneously through superposition. It isn't just about linking those possibilities together through entanglement. It's about carefully sculpting how those possibilities interfere with one another, so that when you finally look, the answer you want is dramatically more likely to be the one staring back at you. Now, it's important to pause here and correct one of the most common misunderstandings about quantum computers, because it matters enormously. A quantum computer is not simply a faster version of your laptop. It will not load web pages more quickly. It will not make your video games run at a higher frame rate. It will not help you scroll through social media any faster. For the vast majority of everyday tasks, a quantum computer would actually be slower and far less practical than the device already in your pocket. The power of quantum computing is not general-purpose speed. It is a specialized, almost surgical advantage that only appears when a problem has a very particular mathematical structure, one where superposition, entanglement, and interference can actually be put to work. Try to use a quantum computer to check your email, and you'd be using a multi-million-dollar refrigerated marvel of engineering to do something your phone already does better. But hand that same quantum computer a problem involving the simulation of molecular interactions, or the factoring of an enormous number, or searching through an astronomically large solution space, and something remarkable happens. Suddenly, the machine that seemed almost comically overqualified for ordinary tasks becomes capable of things no classical computer, no matter how large or how fast, could ever hope to achieve. Let's talk about what those specialized advantages actually look like in the real world, because this is where the story stops being abstract and starts being genuinely exciting. One of the most talked about quantum algorithms is designed for a task called factoring, breaking a very large number down into its prime components. This might sound like a purely academic curiosity, the kind of thing mathematicians argue about in university lecture halls. It is not. It is, in fact, one of the most consequential problems in the entire digital world, because the security protecting your online banking, your private messages, your medical records, and nearly every secure connection on the internet relies on the fact that factoring extremely large numbers is, for classical computers, essentially impossible within any useful time frame. A classical computer trying to break this kind of encryption by brute force would need more time than the universe has existed, even running at full speed. A sufficiently powerful, error-corrected quantum computer running the right algorithm could, in theory, crack that same problem in a fraction of that time. This isn't a distant hypothetical anymore. It's precisely why cybersecurity agencies and standards organizations around the world have spent the last several years racing to develop and roll out new forms of encryption, specifically designed to resist quantum attacks. Encryption meant to remain secure even against a future quantum computer powerful enough to break today's systems. That race is happening right now, quietly, in the background of the technology you use every single day. Then there's another category of problem where quantum computers show extraordinary promise, simulating nature itself. This one might be even more transformative than the cryptography story because it strikes at the very foundations of chemistry, medicine, and material science. Here's the underlying issue. Molecules are quantum objects. The way electrons behave inside a molecule, the way chemical bonds form and break, the way a new drug might interact with a protein inside your body, all of it is governed by the strange rules of quantum mechanics. And that creates a deep irony. Classical computers, built entirely from ordinary bits, are fundamentally clumsy tools for simulating something as inherently quantum as a molecule. As you add more atoms to a simulation, the computational resources needed to accurately model it explode exponentially, the same way the number of possible states of a group of qubits explodes exponentially, just in the opposite, punishing direction. Simulate a handful of atoms, and a classical computer can manage it. Try to simulate a moderately complex molecule with real pharmaceutical relevance, and even the most powerful supercomputers on the planet start to buckle under the strain. A quantum computer, because it is itself built from quantum objects obeying the same underlying rules as the molecules it's trying to simulate, is naturally suited to this task in a way no classical machine could ever be. Researchers have already used quantum hardware to model the genetic structure of viruses, to simulate protein complexes made up of thousands upon thousands of atoms, and to explore chemical reactions with a level of detail that would be impossibly expensive to compute classically. This means faster development of new medicines, more efficient batteries, better solar cells, new materials, with properties we can't even predict yet, all because we finally have a computational tool that speaks the same physical language as the molecules themselves. Quantum computers also show remarkable promise in the world of optimization, the science of finding the single best solution among an enormous number of possible options. Think about a delivery company trying to plan the most efficient route across thousands of stops, a financial institution trying to construct the ideal balance of investments across a portfolio, or an airline trying to schedule crews and aircraft across a global network while minimizing delays and cost. These are problems where the number of possible combinations grows so explosively large that classical computers can only ever find good approximate answers, educated guesses that are close to optimal but almost certainly not perfect. Quantum algorithms, by exploring vast combinations of possibilities simultaneously and using interference to amplify the strongest candidates, offer a fundamentally different way to attack these problems, one that could eventually deliver solutions that are meaningfully closer to truly optimal, saving fuel, time, money, and resources on a global scale. Of course, none of this comes easily, and it's worth being honest about just how difficult it is to build and operate a quantum computer in the real world, because the challenges are just as extraordinary as the potential rewards. Qubits are almost unimaginably fragile. The delicate quantum states that give them their power, superposition, and entanglement can be destroyed by the tiniest disturbance imaginable. A stray vibration, a whisper of heat, a flicker of electromagnetic interference from a device across the room. This fragility is why many quantum computers today are housed inside elaborate refrigeration systems that cool their components down to temperatures colder than the depths of outer space, mere fractions of a degree above absolute zero, in order to keep unwanted noise and vibration from destroying the fragile quantum information before it can be used. Even under those extreme conditions, qubits still tend to lose their delicate quantum state after a very short window of time, and errors can creep in with unsettling frequency. This is why so much of the cutting-edge research happening right now isn't just about adding more qubits to a chip. It's about quantum error correction, clever techniques that use many physical qubits working together to protect and preserve a smaller number of highly reliable logical qubits, shielding fragile quantum information from the chaos of the outside world long enough to actually complete a useful calculation. Progress here has been genuinely remarkable in recent years. Engineers have found ways to monitor the tiny fluctuations inside a quantum processor far faster than ever before, catching and correcting errors in near real time, and multiple research teams have demonstrated that as they scale their quantum systems up, error rates are actually improving rather than getting worse, a critical and encouraging sign that this technology is moving in the right direction rather than hitting a wall. There are also multiple, fundamentally different approaches to actually building a qubit in the first place, and the competition between them is one of the most fascinating races in modern engineering. Some companies build their qubits out of superconducting circuits, tiny loops of metal cooled to extraordinary temperatures where electrical current can flow with zero resistance and exhibit quantum behavior. Others trap individual atoms using precisely tuned lasers, suspending them in space and manipulating their quantum states with extraordinary precision. An approach that offers a natural kind of uniformity, since every atom of the same element is identical in a way that manufactured circuits can never quite match. Still, others are experimenting with trapped ions, photons of light, or even more exotic physical systems, each with its own trade-offs in terms of stability, scalability, and how easily it can be manufactured and controlled. No single approach has definitively won this race yet, and it's entirely possible that different architectures will end up being best suited for different kinds of problems, the way different types of engines are suited to different types of vehicles. What's clear is that the raw number of qubits packed onto a chip is no longer the only metric that matters. How well those qubits are connected to each other, how low their error rates are, and how many meaningful operations they can perform before their fragile quantum states collapse. These factors are increasingly what separates a genuinely powerful quantum processor from one that simply looks impressive on paper. It's worth pausing to gently push back on some of the more breathless claims you might have encountered in headlines. When a quantum computer accomplishes something in minutes that would take a classical supercomputer an almost incomprehensible span of time, it is tempting to declare that quantum computers have officially made classical computing obsolete. That's not quite the reality. These landmark demonstrations, often described as achieving quantum advantage or quantum supremacy, are carefully chosen to showcase a very specific kind of calculation, one deliberately structured to play to the unique strengths of a quantum processor. They are extraordinary proof that quantum computers can, in the right circumstances, achieve something genuinely impossible for classical machines, and that alone is a monumental scientific milestone. But most of these headline-grabbing demonstrations do not yet solve a problem of direct, immediate, real-world economic value. They are proof of concept, spectacular and important proof of concept, showing the world that the underlying physics really does deliver the power theory predicted. But the leap from these narrow demonstrations to broad, industrially transformative applications is still very much a work in progress. Anyone who tells you that quantum computers have already replaced classical computing for practical purposes is getting ahead of the science. And anyone who tells you this technology is decades away from mattering at all is likely underestimating just how quickly the field has been moving in recent years. Because the pace of progress has genuinely accelerated. Processors that once held a few dozen qubits now routinely operate with well over 100, connected by an increasingly sophisticated web of couplers that allow more of them to interact meaningfully with one another. Companies developing neutral atom architectures have announced roadmaps aiming to scale toward tens of thousands, even hundreds of thousands, of individual qubits within a single system. Software tools for programming and controlling these machines have matured substantially, making it easier for researchers outside of specialized physics labs to actually design and run meaningful quantum experiments. Hybrid systems, where a quantum processor works hand in hand with a classical supercomputer, each handling the part of a problem it's naturally best suited for, have emerged as a particularly promising near-term path, one that doesn't require a fully mature, flawless quantum computer to start delivering real, tangible value today. Investment has followed accordingly, with billions of dollars flowing into the field from governments, research institutions, and private companies who are betting, with increasing confidence, that this technology represents one of the next great transformations in human computing capability. There's one more thread worth pulling on, because it ties everything together: the question of who is actually building these machines, and how close we really are to the moment when quantum computers stop being laboratory curiosities and start becoming everyday industrial tools. A handful of major technology companies have poured enormous resources into superconducting qubit architectures, publishing multi-year roadmaps that lay out, almost like a countdown, exactly how many qubits, how many logical operations, and how much error correction they expect to achieve year by year. Alongside them, a wave of smaller, more specialized companies has emerged, each betting on a different physical approach: trapped atoms, trapped ions, photonic systems, even more exotic platforms still being explored in university labs. This diversity isn't confusion about where the field is headed. It's a sign of a technology still young enough that multiple promising paths remain open, the way early aviation saw competing designs before the industry converged on what we recognize today. Governments have taken notice as well, treating quantum computing as a strategic technological priority on par with artificial intelligence, pouring public funding into research consortia, national laboratories, and international collaborations. Because whichever nations and companies master this technology first will hold a substantial advantage, not just economically, but in areas touching national security and scientific leadership. Cloud access has also quietly transformed how this technology reaches the wider world. You no longer need your own refrigerated laboratory to experiment with a quantum processor. Several of the leading quantum computers on the planet are now accessible remotely over the internet to researchers, students, and companies who want to test algorithms, explore new applications, or simply learn how this strange new form of computation actually behaves. That accessibility matters enormously, because breakthroughs in this field are unlikely to come exclusively from the handful of teams building the hardware itself. They are far more likely to emerge from the much larger community of chemists, biologists, financial analysts, and engineers who finally get hands-on access to a genuinely quantum tool and start asking questions specific to their own field. Questions the original hardware builders might never have thought to ask. This democratization of access, even in these early, imperfect, error-prone days of the technology, is quietly laying the groundwork for the moment when quantum computing stops being a niche specialty and becomes a standard part of the computational toolkit, sitting alongside classical supercomputers and cloud computing as just another resource that scientists and engineers reach for when the problem in front of them demands it. So where does that leave us, and why should any of this matter to someone who will probably never personally touch a quantum computer? It matters because the effects of this technology, when it does mature, will not stay confined to physics laboratories. If quantum computers eventually deliver on their promise for drug discovery, the medicine your doctor prescribes in the future might be designed with a level of molecular precision that simply isn't achievable today, developed faster and tested more thoroughly before it ever reaches you. If quantum computers deliver on their promise for materials science, the batteries powering your devices in your car, the solar panels on your roof, the fertilizers used to grow your food, all of these could become dramatically more efficient, addressing challenges around energy and sustainability that have resisted classical computational approaches for decades. And if quantum computers deliver on their darker potential, the potential to break the cryptographic systems that currently protect nearly every secure interaction on the internet, then the quiet, unglamorous work happening right now to build quantum-resistant encryption becomes one of the most important technological safeguards of our era, a kind of digital insurance policy being purchased years before the threat it protects against fully arrives. What makes quantum computers so powerful, in the end, isn't a single trick or a single number climbing higher on a chart. It's the combination of three deeply strange, deeply real phenomena working in concert. Superposition, which allows a system to explore a staggering number of possibilities simultaneously. Entanglement, which binds those possibilities together into a single, coordinated computational fabric, rather than a disconnected pile of guesses. And interference, which sculpts that vast landscape of possibilities so that the right answers rise to the surface while the wrong ones fade quietly away. None of this makes quantum computers better than classical computers in some broad, universal sense. It makes them different, built from an entirely different physical foundation, suited to an entirely different category of problem, one where the sheer scale of possibilities has always been the limiting factor. For those specific problems, the ones involving factoring enormous numbers, simulating the quantum behavior of molecules, or navigating optimization landscapes of staggering complexity, quantum computers don't just offer an incremental improvement over what came before. They offer a fundamentally different way of computing, one capable of achieving in minutes what would otherwise take longer than the universe has existed to accomplish by any classical means. That single fact, once you really sit with it, is one of the most extraordinary achievements in the entire history of human engineering, and we are only just beginning to see what it makes possible.